In the endless dark between stars, where gravity weaves the faintest whispers of motion, something began to move toward us. A shadow, slow and deliberate, older than any human story. It came not from our sun, but from the deep cosmic ocean beyond its light. A fragment of elsewhere, gliding silently into the territory of our star. On the first day of July, in the year 2025, the Atlas observatories of Earth caught sight of it. A faint flicker in the night sky, recorded first as a streak, then as a question. Astronomers named it 3I/Atlas, the third interstellar object ever known to trespass through our solar system. At first, it appeared ordinary, another wandering visitor, like the comets and asteroids that drift endlessly between worlds. Yet the data whispered unease. Its orbit was too precise, its path too aligned with the plane of our planets, as though it had chosen the most efficient corridor through our celestial neighborhood. It shone too brightly for its size, yet no tail trailed behind it. No plume of vapor, no shimmer of dust. Only a cold, mirror-like glint, catching sunlight in ways a lifeless stone should not. For a moment, scientists were still. They had seen something like this before, in 2017, with Oumuamua, another interstellar enigma. But this was different. 3I/Atlas was larger, stranger, more deliberate in its approach. And as it slipped silently into the solar system's heart, past the orbit of Mars, one question began to echo through observatories, universities, and late-night radio frequencies alike. What if this was not a coincidence of nature, but a message, carried by something that remembers where it came from?
It began, as most revolutions in science do, with a flicker of data. A few lines on a computer screen, a pattern that did not belong. In the cool darkness above the Hawaiian Islands, the Asteroid Terrestrial Impact Last Alert System, known simply as ATLAS, watched the heavens as it did every night. Designed to scan for threats, asteroids that could one day descend upon Earth, it captured thousands of moving points of light each hour. Most were ordinary, fragments of rock, ancient ice, satellites, and debris. But in the early hours of July 1st, 2025, a faint signature appeared that did not fit. It moved too fast, too cleanly. Its orbit was not one of this solar system. Within minutes, the algorithms flagged it as unbound, a visitor traveling not in an ellipse, like a planet or comet, but on a hyperbolic trajectory. The mathematical fingerprint of an interstellar traveler. Its eccentricity, a value that defines how stretched an orbit is, was greater than 1, confirming that it would not stay. This object, whatever it was, had come from the stars and would soon return to them. The catalog designated it 3I Atlas, the third confirmed interstellar object ever detected by humankind. The I stood for interstellar, a symbol that carried both scientific precision and poetic weight. Before it, there had been only two. In 2017, 1I Oumuamua, the mysterious tumbling shard that reflected sunlight like a mirror and accelerated without a tail. In 2019, 2I Borisov, a true comet from another star, whose icy coma confirmed the existence of frozen worlds beyond our own. But 3I Atlas was different. It seemed to hover in the uneasy space between those two worlds. Neither comet nor rock, familiar yet alien. At the University of Hawaii, astronomers gathered to refine its orbit. Using data from multiple observatories, they traced its path backward through space, searching for a point of origin. The results defied simplicity. Its approach vector came from the direction of the constellation Serpens Caput, far above the plane of our Milky Way's equator. Its heliocentric velocity, relative to the Sun, measured at nearly 26 kilometers per second, faster than any asteroid could be ejected from our system naturally. Its trajectory was astonishingly aligned with the ecliptic plane, the thin cosmic sheet upon which the planets circle the Sun. Such alignment is rare for interstellar visitors. whose paths usually slice through the solar system at random angles. The odds of this precision, of an alien object arriving exactly along the plane of Earth's orbit, were so improbable that some wondered whether it had been guided. At Harvard University's Center for Astrophysics, theoretical physicist Avi Loeb received the early data. Loeb was no stranger to controversy nor to wonder. He had once proposed that Oumuamua might have been an artificial probe, a relic of alien engineering propelled by radiation pressure rather than chemical thrust. That idea had divided the scientific community. But now, as he studied the new object's trajectory, he felt a familiar tremor of curiosity. Working with collaborators Adam Hibbard and Adam Crowell, Loeb began to model its path using orbital mechanics and dynamical simulations. The numbers resisted ordinary explanation. 3I Atlas, they calculated, would pass closer to the Sun than Mercury in late October of 2025, slingshotting around the inner solar system before heading outward again, near the orbit of Jupiter by the spring of 2026. Yet its entry path, the precise way it had threaded itself into the solar system's geometry, was what caught their attention. It wasn't chaotic, it was elegant. The team calculated that the probability of such an alignment occurring randomly, given the vast openness of interstellar space, was less than 1 in 10,000. For Loeb, who had long argued for cosmic modesty, the idea that humanity should not assume it is unique, the implications were staggering. If 3I Atlas was natural, it would expand the known diversity of interstellar debris. But if it wasn't, if its trajectory had been chosen, then Earth might, for the first time, be witnessing an artifact of another civilization crossing into our neighborhood. While Harvard and other observatories ran simulations, the Atlas network continued to gather images. Night after night, the object brightened slightly as sunlight reflected off its surface. But there was something missing. No coma, the halo of evaporating ice that forms around a warming comet, was visible. No tail stretched behind it, even as it drew nearer to the sun. Its spectral profile, when analyzed through instruments at Mauna Kea and later by the European Southern Observatory, showed no clear fingerprints of water vapor, carbon monoxide, or cyanide gas. It was, in every measurable sense, inert. And yet, it gleamed, far brighter than a body of its estimated size should. The data hinted at a high albedo, or surface reflectivity, perhaps similar to polished metal or fine-grained silicate. The shape was still uncertain. Its light curve, the rhythmic brightening and dimming as it rotated, was erratic, suggesting either an irregular form or a tumbling motion. Astronomers proposed models: an oblong rock, a dark comet coated in dust, a fragment of planetary crust torn from a dying world. But each model failed one crucial test. None could explain its brightness and lack of volatile outgassing at such proximity to the sun. It was as though the object had been sealed, designed to resist evaporation, to endure the heat unscathed. As days passed, the story of 3I Atlas began to spread through the scientific community, then into the public sphere. Forums buzzed with speculation, news outlets with half-truths and hope. But behind closed doors, astronomers were more cautious. They had seen how easily a discovery could turn mythic, how quickly human longing could shape an observation into a prophecy. And yet the data would not quiet itself. When cross-referenced with its expected future trajectory, analysts noticed another peculiarity. 3I Atlas was set to pass near Earth's orbital path, though still millions of kilometers away, before curving inward toward the sun. It was, by cosmic measure, a near miss. Enough for radio astronomers to suggest scanning it for artificial emissions. just as they had once done briefly with Oumuamua. So far, there was silence, only reflected sunlight, whispering across the void. As the month wore on, the object grew faint once more, slipping towards solar conjunction, the period when it would vanish behind the sun's glare. It would not be visible again until late autumn. Scientists raced to capture every last photon before it disappeared. The data archives, filled with numbers, photometric brightness, astrometric positions, minor deviations in path. Each value carried within it a question larger than itself. Could interstellar space really be filled with such travelers? Was 3I Atlas merely the first we had the fortune to notice? Or one of many, each crossing unseen? And if it was one of many, why did this one seem to notice us? In laboratories and observatories, researchers ran models through supercomputers, charting millions of simulated trajectories. Most ended in randomness, fragments flung by dying stars, remnants of collisions in alien systems. But a small fraction, an uncomfortably persistent fraction, produced orbits indistinguishable from 3I Atlas's path. Only when an artificial component was added. A light sail, perhaps, reflecting sunlight as propulsion, or a thin, metallic hull deflecting radiation. For now, these were only speculations, thought experiments that tested the boundaries of plausibility. Yet the numbers held their shape. They refused to vanish into the noise. By the time 3I Atlas slipped beyond the reach of most ground-based telescopes, a quiet consensus had formed among those who watched the skies most closely. This was a discovery unlike any before. Not because it promised alien contact, but because it shattered the fragile assumptions that humans held about isolation. The solar system, it seemed, was no longer a sealed world. It was a crossroads, an open thoroughfare, where matter and perhaps even memory drifted in from the stars. The discovery of 3I Atlas did more than expand the catalog of known objects. It expanded the horizon of what could be imagined. By late July, the numbers no longer whispered mystery, they screamed it. Every measurement, every reflection, every photon from 3I Atlas defied what the universe was supposed to be. Astronomers had expected something familiar, an icy wanderer, a dirty snowball flung from another sun. Like 2I Borisov, whose coma of gas and dust confirmed it as a true comet from a distant cradle of light. But Atlas was silent. Its surface shone without melting, without sighing a single breath of vapor into space. No coma, no tail, no spectral trace of ice sublimating into sunlight. In a universe where every comet sings through the language of evaporation, this one refused to speak. At first, researchers at the Center for Astrophysics dismissed it as a trick of geometry or distance, a phase angle illusion perhaps, or faint activity too subtle for early detection. But as telescopes in Chile, Spain, and Hawaii combined their gaze, the conclusion grew harder to ignore. The object was dry, devoid of volatiles. Its brightness was steady and metallic, as though light slid across a polished surface rather than scattering through dusty haze. It was not behaving like a comet. It was not behaving like an asteroid. It was behaving like something else entirely. The first orbital refinements brought a deeper unease. 3I Atlas was moving through the solar system on a low-inclination trajectory, almost perfectly aligned with the ecliptic plane, the thin cosmic sheet upon which the planets orbit the sun. Such precision was uncanny. Interstellar objects, by all probability, should arrive at random inclinations, cutting sharply through the solar system's plane like stray bullets. Yet this one seemed to glide effortlessly along it, almost as if it had been aimed. When statistical models were run, millions of Monte Carlo simulations of random arrivals, the likelihood of such an alignment emerged as less than 5 in 100,000, 0.005%. The object's journey through the inner solar system only deepened the mystery. Its projected path threaded improbably close to Venus, skimmed within a few million kilometers of Earth's orbital path, then arced outward toward Jupiter's gravitational domain, a near-perfect sequence of planetary encounters that, by random chance, bordered on impossible. Celestial mechanics allows for coincidence, but rarely for choreography. As its distance shrank and its reflected sunlight intensified, astronomers could at last estimate its physical dimensions. Based on its apparent magnitude and assumed albedo, the numbers place 3I Atlas at roughly 150 to 200 meters across, perhaps more, significantly larger than Oumuamua, which was estimated at barely 100 meters long, and denser in reflectivity than any known natural interstellar body. But what truly stunned researchers was not its brightness, it was its behavior. Precise astrometric data revealed minute deviations in its motion, a subtle drift not entirely consistent with gravitational predictions. These non-gravitational accelerations were faint but measurable, tiny nudges in velocity as though some unseen force pushed gently against it. With Oumuamua, such accelerations had once been attributed to outgassing, jets of sublimating ice creating a faint, invisible thrust. But 3I Atlas exhibited no such mechanism. Its spectrum was flat, its temperature stable. No jets, no vapor, nothing that could explain the acceleration. And so, quietly at first, then more openly, a familiar question began to rise again. The same question that had haunted the scientific community since 2017. What if it isn't natural? At Harvard, Avi Loeb and his collaborators revisited their models. If sunlight alone were responsible for the acceleration, the object's mass-to-area ratio would need to be extraordinarily low, comparable to that of a light sail, a thin sheet capable of catching photons like wind. The math aligned unsettlingly well. A surface thickness of less than a millimeter could account for the measured thrust. Not impossible for nature, but deeply improbable. Such thin, broad structures do not survive the interstellar medium intact. Micrometeoroids, radiation, and cosmic dust would shred them across light years of travel. Unless, of course, they were designed to endure. It was a hypothesis few dared to voice aloud. And yet, in the data, the possibility refused to die. The Center for Astrophysics, the SETI Institute, and numerous independent researchers began reviewing alternative explanations. Could it be a fragment of a shattered exoplanet? A metallic remnant stripped from a dying system? Could the acceleration arise from thermal recoil? An uneven distribution of heat radiating from its surface? Each answer solved one puzzle only to raise another. If it were a planetary fragment, why the perfect trajectory? If thermal recoil drove it, why was its albedo so high and uniform? If it were natural, why did it behave as though it had intent? The debate fractured into two schools of thought. Those who sought to stretch known physics until it could contain the anomaly, and those who quietly wondered if the anomaly was stretching physics itself. The New York Post, among others, seized on the story. Harvard scientists study strange object that could be alien probe, the headlines read. Crude echoes of the cautious curiosity that defined the scientific discussion. But behind the noise, in the quiet hum of observatories and the late-night glow of computer screens, the real question ran deeper, quieter, more intimate. If this was artificial, then what did it mean? Because artificiality implied agency, and agency implied someone, Even for those who dismissed such speculation, the implications remained staggering. If Three-Eye Atlas were natural, then our understanding of cometary physics was incomplete. The very taxonomy of celestial visitors, comets, asteroids, interstellar debris, would need rewriting. There might exist a whole new class of objects: dry, dense, reflective, unyielding to sunlight. Interstellar fossils of processes not yet understood. But if it were not natural, if it were engineered, then the consequences reached far beyond science. The solar system, long thought to be isolated within a sterile void, would no longer be merely an astronomical address. It would be known. Philosophers once said that the universe is silent because no one else is listening. But silence itself can be a form of communication, a message written in absence. Perhaps Three-Eye Atlas was not a voice, but an echo, a drifting artifact, long dead, carrying within it the memory of a civilization erased by time. Or perhaps it was something simpler still. A seed, a sensor, a lost fragment of exploration, cast adrift by minds who, like us, once wondered if they were alone. Its silence was not indifference. It was endurance. Within the data, humanity faced a kind of mirror. For centuries, the cosmos had been a backdrop to our questions, a canvas on which we painted our ignorance. But this was the first time the universe seemed to respond. Not with an answer, but with a question of its own. What if the boundaries we assume between nature and technology are illusions? What if intelligence itself is a cosmic force recurring across eons like gravity or light? The discovery of Three-Eye Atlas forced scientists to confront not just a mathematical anomaly, but an existential one. If a relic of alien engineering could cross into our skies unnoticed until the last moment, what else might drift between the stars? What else might already have passed, unseen? By the close of the summer of 2025, the world's observatories had done all they could. The object was now too near the sun to observe safely. It would vanish into the solar glare for months. The data, however, remained, a trail of numbers that refused to settle. Somewhere in those figures lay the truth. The thermal inertia, the spectral flatness, the trajectory that seemed to hum with purpose. But truth, like light, often bends before it reaches the eye. And so the scientists waited for the next observation window, for confirmation or contradiction, for clarity or for the unraveling of their own certainty. In the quiet between signals, the realization sank in. The shock was not only scientific, it was existential. For in a single silent visitor, dry, bright, and impossibly aligned, humanity had glimpsed something vast, a hint that intelligence might not be unique to flesh and thought, but woven into the machinery of the cosmos itself. And though Three-Eye Atlas would soon vanish beyond the sun, its presence would linger, like a question that could not be unasked. A comet or not a comet? A visitor or a messenger? The universe had spoken again, and this time, its silence was deafening. By the end of August 2025, the world's telescopes had turned toward a single point in the sky, a silent traveler whose faint reflection carried whispers from another star. Every observatory, every instrument capable of piercing the darkness joined the effort. From Mauna Kea to Cerro Paranal, from the Pan-STARRS array in Hawaii to the Very Large Telescope in Chile, the Earth itself seemed to hold its breath, watching a fragment of interstellar night drift closer to the sun. Three-Eye Atlas had become more than an object. It was now a mirror, reflecting not just sunlight, but the limits of human understanding. Photometric data began to flood in. Stacks of exposures. Hours of light collapsed into single spectral signatures. Each photon was weighed, measured, compared. The light curve was smooth, consistent, almost eerily so. No flicker, no irregular spin. Where comets rotate erratically and shimmer with volatile jets, 3I Atlas remained steady, as though its shape and surface were unnaturally uniform. Spectroscopic analysis came next. Scientists tuned their instruments to the wavelengths of water ice, carbon monoxide, cyanides, ammonia, and metal lines, the familiar vocabulary of cometary chemistry. But the spectra were silent. No signatures of outgassing. No emission bands from sublimating ice. No spectral absorption from water or hydroxyl radicals. Instead, there was an unusual reddening of light. Not the warm reflection of dust or iron oxide, but a deep, metallic redshift, suggestive of processed material, perhaps irradiated metal or carbon composites baked by eons of interstellar travel. In a Medium article, published by Harvard astrophysicist Avi Loeb, the analysis was summarized simply. 3I Atlas lacks the fingerprints of a natural comet. The world's largest eyes turned toward it. The Keck Observatory, the European Southern Observatory's VLT, and even the James Webb Space Telescope, though not originally purposed for such fleeting visitors, contributed partial spectra, capturing scattered photons before the object slipped too close to the sun's glare. Meanwhile, radar facilities, Goldstone, Greenbank, and others prepared to attempt contact when the geometry allowed, though the object's faint radar cross-section and high velocity rendered the chances slim. The Mars Reconnaissance Orbiter, whose instruments can sometimes detect cosmic visitors from its vantage point, was repurposed briefly for monitoring. Even the Juno spacecraft, orbiting Jupiter, was tasked to record background particle variations, in case the interstellar object's path intersected the solar wind in an unexpected way. This global orchestration of instruments marked one of the rare moments when the planet's scientific community acted almost as a single organism, coordinated, silent, patient. But the more data they gathered, the deeper the riddle became. By September, thermal models predicted that at its current approach distance, 3I Atlas should have been shedding material, tiny grains of dust at least, as sunlight heated its surface beyond 150 Kelvin. Yet the instruments found nothing. No dust trail, no thermal emission. Instead, its surface temperature remained remarkably stable, as though insulated or self-regulated. Polarimetric readings revealed something even stranger: negative polarization, a reflection pattern inconsistent with natural rocky or icy materials, but more typical of metallic or composite surfaces. Astronomers speculated on its composition. Could it be high nickel alloy, partially oxidized, or laced with carbon-based compounds hardened by cosmic radiation? The metal ratio analysis, inferred from minute color differentials, suggested a skew toward nickel and iron, with low cyanide and silicate presence. Whatever it was, it had the spectral personality of manufacture, not geology. The next frontier was astrodynamics, the mathematics of motion. Astrophysicists modeled its acceleration patterns, using data from ATLAS, Pan-STARRS, and ESA's Gaia satellite to track its position to within fractions of an arcsecond. What they found blurred the line between celestial mechanics and intent. Its trajectory, though hyperbolic, contained subtle deviations that could not be easily explained by gravity alone. The curve of its flight resembled a calculated path, one that used planetary gravity wells almost deliberately, a series of near passes that resembled an Oberth maneuver. the technique by which spacecraft use a planet's motion and gravity to amplify speed with minimal energy. A natural rock would have no such purpose. But this object seemed to move with quiet efficiency, as though obeying equations of design rather than chance. Models placed its perihelion, the closest approach to the Sun, on October 29, 2025, a date that would soon become the focal point for the entire astronomical community. Beyond that, its projected outbound trajectory suggested a close pass by Jupiter in March 2026, offering a final window for observation before it vanished into the galactic dark once more. Between those two milestones, telescopes worldwide would track it relentlessly, the last dance before disappearance. Yet even as instruments captured light and data, the debate grew sharper. Some researchers proposed the dark comet model, a rare type of comet so depleted in volatiles that it produced no visible tail, its surface crust hardened and sealed by millennia of cosmic radiation. These bodies, they argued, could mimic asteroidal appearances while still being entirely natural. Others countered. The alignment, the non-gravitational thrust, the metal ratios, the polarization, all combined into a pattern too specific to dismiss. If it were natural, it was unique among millions of catalogued bodies. Harvard's Avi Loeb, joined by researchers Adam Crowell and Adam Hibbard, posited an alternate hypothesis: that 3I Atlas might represent a fragment of interstellar technology, perhaps a derelict probe or a wafer-thin solar sail ejected long ago by another civilization. Their papers did not claim proof, only possibility. But possibility was enough to reignite the debate that had begun 8 years earlier with Oumuamua. Could it be that our solar system is not a sealed chamber, but a crossroads? By October, solar conjunction began, a period when 3I Atlas passed behind the Sun from Earth's perspective, blinding telescopes and cutting communication. It was a time of enforced waiting. The object slipped into the solar glare, invisible, its trajectory now carried only by prediction. During that silence, scientists pored over terabytes of data already gathered, refining brightness models, recalculating orbital perturbations, adjusting for solar radiation pressure. Each new fit narrowed the uncertainty, yet widened the enigma. Even NASA's Planetary Defense Coordination Office, accustomed to modeling asteroid impacts, joined in, ensuring that no gravitational anomalies hinted at unknown masses or hidden forces. Nothing emerged except the same impossible precision that had haunted the data since July. In private meetings, behind closed observatory doors, the tone of discussion shifted. No one wished to declare the extraordinary, but neither could they dismiss it. The deeper they peered, the more it seemed that 3I Atlas existed in a gray space between nature and artifice, a ghost in the equations, as if the universe itself were testing human reason. Was it the product of cosmic randomness, a sculpture carved by entropy and time, or a relic of purpose, lost to the void long before humanity learned to speak? The data could not answer, it could only whisper. And yet, even in the absence of certainty, the search continued. Because discovery is not merely the pursuit of answers, it is the act of confronting the unknown and refusing to look away. In that sense, 3I Atlas had already achieved something profound. It had united the species, not in fear, but in wonder. For as it drifted toward its fiery encounter with the Sun, invisible now to our eyes, the question it carried remained luminous. What if the cosmos is not merely a wilderness of chance, but a conversation, waiting for minds capable of listening? When 3I Atlas would re-emerge from behind the Sun months later, No one knew what they would find. Perhaps it would behave as a comet at last, flaring with vapor and dust. Perhaps it would remain silent, reflecting only what we project upon it. But one truth was clear. Every observation, every model, every spectral silence had deepened the mystery rather than dispelled it. And as the telescopes cooled and the data archives filled, the world waited once more for a signal, for a glint of truth.
By late October of 2025, 3I Atlas had vanished into the brilliance of the sun. Its light, once measured, analyzed, and dissected by every telescope on Earth, was now swallowed by solar glare, beyond the reach of human instruments. For months, astronomers had traced its path toward this moment, perihelion, the point of closest approach to our star. At precisely 29 October 2025, it would graze the sun's domain at a distance of little more than 0. 3 astronomical units, closer than Mercury's orbit, deep within the furnace of radiation and gravity. To most celestial visitors, such a passage meant death, disintegration under solar heat, fragmentation into dust. But for some, it could mean something else. For a spacecraft, a close solar pass is not destruction, it is opportunity. The timing unsettled many. For those who had long speculated that 3I Atlas might be artificial, this was the moment to watch. In human spaceflight, the O-berth maneuver is a legendary trick of physics, a slingshot through a gravity well that multiplies speed by burning energy at the point of deepest gravity. But theorists at Harvard and ESA began to model something more subtle, a reverse O-berth, a deliberate deceleration using solar radiation pressure and orbital geometry to shed velocity instead of gain it. If 3I Atlas were technological, a probe, a sail, or something older still, perihelion would be the perfect stage for such a maneuver. The gravitational potential of the sun could be used not to escape faster, but to linger longer in the inner solar system. The very notion raised unease. If it slowed, where would it go? What would it be waiting for? At the Center for Astrophysics, teams simulated every conceivable trajectory beyond October 2025. Using Monte Carlo models and NASA's JPL Horizons data, they ran tens of thousands of possible orbital outcomes, none predictable with certainty, all branching from subtle, non-gravitational accelerations. In a handful of simulations, less than 0.2%, the object's trajectory altered slightly after perihelion, adopting a gentler outbound arc, rather than the expected hyperbolic escape. A deceleration so small it could hide within measurement error, yet large enough, if real, to change its destiny. To natural physics, such a maneuver would require forces no comet could produce. To human technology, it would require design. And so, in papers, in late-night calls, and whispered exchanges between observatories, the question began to take shape. Could 3I Atlas be doing something? In the weeks that followed, speculative models emerged in the quiet corners of the scientific internet. Some proposed that the object might deploy sub-probes, releasing smaller fragments optimized for planetary flybys, a reconnaissance network scattered through the inner solar system. Others envisioned solar braking sails, devices capable of catching the sun's photons to slow down and establish long-term orbits. In academic circles, the tone remained cautious, but the tension was palpable. For the first time, a natural visitor from beyond the stars was being discussed not merely as an object, but as an actor, capable perhaps of intention. The emotional undercurrent grew heavier still when comparisons were drawn to the dark forest hypothesis. The idea, proposed by astrophysicist Lu Cixin, that advanced civilizations may remain silent not out of isolation, but self-preservation. That every technological signal risks revealing itself to predators in a cosmic wilderness. If so, then 3 Atlas silence might not be absence. It might be caution. In the halls of the Center for Astrophysics, some scientists argued against alarm. No data yet suggested emissions, communication signals, or directed energy outputs. The radio arrays at Arecibo's successors, Meerkat in South Africa and FAST in China, were tuned to the frequencies around the object's coordinates. Nothing but the usual cosmic background noise. But the lack of signal only deepened the intrigue. For if it were artificial, what reason would it have to speak? Perhaps it already had, not in radio, but in motion. Trajectory, after all, is a language of intent. In the absence of real-time observation, the theoretical community fractured. Some, like Loeb and Hibbard, argued for openness, that science must not censor extraordinary possibilities simply because they seem uncomfortable. Others cautioned restraint, warning against a descent into pseudoscience and spectacle. Yet even the skeptics found the object's silence unsettling. Every day it lingered behind the sun, invisible. The collective imagination of the planet filled the void with meaning. Would it reappear exactly where celestial mechanics predicted? Or would it emerge elsewhere, on a trajectory no model could explain? By mid-November, as solar conjunction neared its end, radio observatories prepared for reacquisition. Arrays across the world synchronized, from Hawaii's Haleakala to the European Southern Observatory's La Silla, from NASA's Deep Space Network antennas to Japan's ALMA radio telescopes. And as the world waited, the anticipation shifted from scientific curiosity to existential reflection. What if humanity's first true encounter was not a transmission or a landing, but a pattern, a movement through light, a signature written in celestial geometry? If 3i Atlas were indeed an ancient craft, it might not be visiting us at all. It might be following a mission older than our species, an automated journey set in motion long before the Earth had names for the stars. Or worse, it might be observing, a quiet sentinel, cataloging a young civilization just learning to look back. The idea of risk crept into public consciousness. News outlets began to echo the scientific murmurs. Could this object pose a threat? Not by impact. Its trajectory posed no collision danger, but by something subtler, knowledge. If 3i Atlas was artificial, then somewhere out there existed a maker, a civilization capable of building objects that could cross the void between suns, endure for millennia, and navigate gravitational wells with the precision of thought. The universe, once cold and empty, suddenly seemed alive, aware, and humanity, in that reflection, felt smaller than ever. Behind the tension, however, another current flowed, one not of fear, but of awe. Because whether 3i Atlas was natural or not, its very existence was rewriting what humanity understood about cosmic wanderers. It challenged the old categories, asteroid, comet, interstellar rock, and demanded something new. Perhaps there exists a continuum between the organic and the engineered, where natural forces and intelligent design blur into one. Perhaps technology, too, is an evolutionary process of the cosmos, not an anomaly, but a phase. If that were true, then objects like 3i Atlas might not be intrusions at all. They might be inevitable. At Harvard, a quiet phrase began to circulate among the research teams: science at the edge of its map. For centuries, humanity's tools had expanded its horizons. Telescopes that see the past, probes that drift beyond the planets, detectors that listen for gravitational ripples. But every tool assumes a framework, a reality with rules. 3i Atlas did not break those rules. It merely revealed how small they might be. In its silence, it seemed to whisper that discovery is not about conquering mystery, but coexisting with it, accepting that the universe may always contain phenomena that sit just beyond comprehension, inviting but never answering. When the measurements settled into their stubborn shapes, dry spectra, bright skin, careful trajectory, the human mind did what it has always done at the edge of comprehension. It told itself two stories. One spoke in the language of geology and ice, the other in the grammar of intention. The first story is the oldest, the natural comet hypothesis, recast for an interstellar age. In this telling, 3I Atlas is a dark comet, a relic stripped of its showiness by time. In the violent nurseries of other suns, bodies coalesce and shatter. Fragments are flung outward by the restless choreography of giant planets. Some wander for eons between stars, their outer layers baked by radiation, their ices sealed beneath a crust of carbonized dust. By the time such an object nears a star again, its surface may be devolatilized, a hardened rind through which heat cannot easily wake the ancient frost below. No coma then, no tail, only a sullen gleam and a silence that looks like refusal. There are variants to the same refrain. Perhaps the body formed with a refractory, rich composition to begin with, poor in water and carbon monoxide, seeded instead with silicates and metals that do not easily sublime. Perhaps it carries ices, but micron-scale dust mantles the surface tightly, confining vapors to a porous underworld where pressure vents never crack. In such a case, the feeblest non-gravitational forces might arise from microjets that are too small and too transient for telescopes to register, yet sufficient to curve a path by millimeters per second over months. The strengths of this hypothesis are familiar and comforting. It requires no new physics, no unseen actor, no revision to the cosmic order beyond an expansion of known diversity. Interstellar space should be littered with debris. A subset ought to be old, insolent, and quiet. The absence of classic gas signatures may reflect observational limits. Phase angles unfavorable for detecting faint comet, spectra diluted by solar glare, dust too coarse to scatter light. But the hypothesis carries its own unease. Its cons are cut from the data's sharper edges. A brightness that seems high for an inert body, polarization behaviors that imply unusual surface microstructure, trajectory fine-tuning that hugs the ecliptic as if taught to do so. It explains parts of the portrait, it leaves others smudged. Likelihood becomes a moving target, a probability updated with every photon, never collapsing into certainty. The second story does not dismiss nature. It expands it to include technology, an outcome of nature's own long game. In this view, proposed most prominently by Avi Loeb and collaborators, 3I Atlas could be artificial, a probe, a sail, a fragment of engineered material whose properties, low mass-to-area ratio, specular reflectance, persistent dryness, are features, not bugs. Its low inclination trajectory and sequence of close planetary passages look less like coincidence and more like navigation. Its subtle non-gravitational acceleration reads like a whisper of thrust without fuel. If such a hypothesis is entertained, a cascade of physics implications follows, none of them supernatural, all of them difficult. The simplest driver is radiation pressure, photons imparting momentum to a thin surface. To achieve the observed accelerations with sunlight alone, the structure's aerial density would need to be small, comparable to a light sail, perhaps sub-millimeter thick. Materials science offers candidates, aluminized polyamides, graphene composites, metamaterial films engineered to manage heat while reflecting strongly in visible wavelengths. Over interstellar timescales, these films would face micrometeoroid erosion and charging. Surviving intact would imply either redundancy, large sail, small tears tolerated, or self-healing architectures unknown to present engineering but plausible in principle. Beyond passive sailing, there is the specter of active thrust, too subtle for current instruments to distinguish from radiation pressure. A colloid electric sail pushing against the solar wind, for instance, or photophoretic effects on structured surfaces that create minute net forces when temperature gradients are maintained. Closer to perihelion, thermal desorption of engineered coatings could provide a controlled, low-signature impulse, behavior that would masquerade as cometary outgassing, while obeying design rather than chemistry. Guidance is the more haunting question. To choreograph a path along the ecliptic and exploit gravity assists with the serenity implied by the data, an onboard system would need to sense position and adjust accordingly, perhaps not in real time, but through pre-computed windows, nudging at milestones where tiny course corrections bloom into vast downstream changes. This is navigational astrodynamics as art, using the sun not merely as a lamp, but as a machine. If artificial, what then of purpose? The spectrum of credible speculation ranges from Bracewell probes, autonomous interstellar sentinels meant to watch and wait, to archaeological debris, the flotsam of exploration shed by missions too old to remember their makers. Some models imagine distributed observing, a primary vehicle shedding micro-instruments at perihelion to seed long-lived orbits, silent archives that could outlast civilizations. Others view the craft as pure transit, a courier that has crossed many suns and will cross many more, its brief alignment with the ecliptic of this system, nothing more than an efficient path discovered by minds that solved celestial mechanics as a language. These possibilities do not overturn physics. They test its limits. Einstein's relativity still binds trajectories. Thermodynamics still taxes every maneuver. But engineering at scale, with materials and control that skirt the edge of detectability, could produce behavior that mimics anomalies while remaining obedient to known law. Beyond mechanism lies context, the large questions that curl behind the small ones. The Fermi paradox remains the quiet drumbeat. If the galaxy is old and fertile, where is everyone? Perhaps they are absent, perhaps they are quiet, or perhaps evidence is subtle by design, not beacons, but breadcrumbs, techno-signatures embedded in dynamics, reflectance, statistics. In such a view, the astronomy of the coming century becomes cosmic archaeology, not a search for voices, but for artifacts whose makers no longer speak or choose not to. The dark forest hypothesis casts a longer shadow. Its survival favors silence, then probes might be watchers rather than talkers. Their emission discipline absolute, their presence betrayed only when patrol routes intersect the gaze of a young species that has just learned to keep records. In this frame, 3I Atlas is not a scout of conquest, but a sentinel of caution, a machine that knows how to hide in plain trajectories. Yet there is a gentler cosmology too. Intelligence may be rare, but persistent. Emergent wherever complexity gets time. Civilizations rise and fall. Their machines endure. Long-lived probes, durable, modest, patient, could be the true ambassadors of minds that never meet, crossing stellar neighborhoods while stars drift like slow lanterns. If so, the galaxy's silence is not empty. It is full of memory. There are more speculative branches, each kept honest by physics. Multiverse frameworks do not send craft across brains, but they remind that selection favors conditions where exploration becomes possible. Quantum engineering need not violate causality to enable single photon navigation or ultra-low power computation aboard a wafer-scale craft. Relativistic beaming is irrelevant at 26 kilometers per second, but special relativity still shapes how tightly time and accuracy must be budgeted for a vehicle to strike gravitational windows across decades. None of this demands miracles. It demands time, discipline, and intent, somewhere in the long fabric of the Milky Way. Between these stories, Dark Comet and Silent Craft, lives the discipline of probability. Priors matter. Nature is prolific. Technology, as far as data shows, is singular. Ours. A Bayesian mind assigns weight to the mundane and taxes the extraordinary. And yet, each anomalous datum nudges the posterior, the ecliptic alignment, the steady brightness without coma, the minute acceleration unaccompanied by gas. Individually, each can bend toward the natural. Together, they lean, gently, not decisively, toward the engineered.
In the months after its discovery, 3I Atlas became not just an interstellar object, but a cosmic experiment. A question cast across every telescope on Earth and beyond. It was no longer enough to observe. Humanity would have to listen, measure, and wait with instruments tuned to the silence of deep space. At the Center for Astrophysics in Cambridge, at JPL in Pasadena, and across observatories spanning Chile, Hawaii, the Canary Islands, and South Africa, researchers began drafting a choreography of observation. A timeline extending years ahead, meant to catch every motion of the visitor before it vanished forever into interstellar dark. They began with what was already awake, the Atlas Survey Network, whose faint detection had birthed the mystery. Next came Pan-STARRS, Subaru, and the Very Large Telescope, their mirrors gathering spectral whispers of sunlight, reflecting off an alien surface. In those spectra, scientists sought clues, the faint fingerprints of water ice, organic compounds, silicates, or perhaps something more structured, anomalous reflection patterns hinting at metals or composites. None appeared with certainty. The data spoke of reddened hues, an interstellar tan born of radiation, but no gas emission lines, no telltale CN, OH, or C2 signatures that betray a living comet. The silence of chemistry deepened. Attention then turned to photometry, the rhythm of brightness as the object spun. With each rotation, the reflected light rose and fell, tracing a pattern like a distant heartbeat. If the pulse was regular, it would reveal shape and spin. If chaotic, perhaps tumbling, the erratic motion of an ancient shard. Early readings suggested a faint periodicity, but the amplitude of variation was small. Either 3I Atlas was nearly spherical, or its surface reflected light evenly across multiple facets, an oddity, since nature rarely polishes in perfect symmetry. Polarization studies followed. By measuring how sunlight scattered off the object's surface, astronomers could infer texture and composition. Dusty comets usually polarize strongly, metallic or dielectric surfaces less so. The result: negative polarization, light returning strangely aligned, as though the surface were composed of microscopic plates or films, rather than grains of dust. To some, it was the fingerprint of a dense, structured material. To others, just another of nature's unpredictable inventions. But the most pressing questions about mass, density, and trajectory required precision impossible from one vantage point alone. So the solar system itself was enlisted. The Juno spacecraft, still orbiting Jupiter in 2026, became a silent sentinel. If 3I Atlas's path brought it anywhere near Jupiter's magnetosphere, Juno's instruments might glimpse the visitor against the planet's background radiation, or sense perturbations in the plasma environment, subtle disturbances caused by the object's interaction with solar wind. NASA engineers quietly adjusted mission schedules, not to chase the object, but to listen in its direction during the approach window of March 2026. Meanwhile, the JUICE mission en route to the Jovian system under ESA command was asked to include contingency pointing routines. Its cameras, designed to study Europa and Ganymede, could perhaps capture faint light curves during the object's outer passes. It was a long shot, but in cosmic investigation, every photon counts. Further afield, the James Webb Space Telescope remained a wild card. With its infrared vision, Webb could detect faint thermal emissions from 3I Atlas's surface, if the geometry allowed. But a complication loomed. By October 2025, at perihelion, the object would pass almost directly behind the Sun from Earth's perspective, a period of solar conjunction lasting weeks. It was the worst timing for observation, and, some whispered, the best moment for maneuver if the object was controlled. As the data accumulated, so did human plans, not all of them purely scientific. At NASA's Planetary Defense Coordination Office, scenarios were quietly drafted. None involved panic, but each explored the improbable. If 3I Atlas were to alter its trajectory suddenly, executing a burn, an unexpected change in velocity, how quickly could the world respond? Radar tracking by Goldstone or Greenbank might detect micro changes in distance. SETI arrays, like those at Breakthrough Listen in California and the Meerkat network in South Africa, could sweep its direction for narrow-band signals, artificial beacons, even encrypted noise. Military satellites, too, would keep an eye open, though for different reasons. An object that could maneuver among planets was no longer a curiosity. It was a potential actor in near-space dynamics. Even without intent, a close pass could trigger gravitational interactions, altering the orbits of minor bodies, or, at extreme probabilities, impact trajectories centuries ahead. In this way, 3I Atlas became the intersection of astronomy and existential preparedness, a test not only of observation, but of collective composure. For the scientific community, the plan unfolded like an orchestra of instruments over time. 29th October 2025. Perihelion. The object behind the Sun, unreachable by most telescopes. A window of suspense. December 2025. Closest approach to Earth's orbit. Roughly 0.3 astronomical units away. Ground-based photometry and radar attempts resume. March 2026. Jupiter flyby window, with Juno and JUICE monitoring potential interactions. Late 2026 and beyond, departure toward interstellar space, faint but traceable with the Vera C. Rubin Observatory, whose legacy survey of space and time, LSST, will catalog every transient dot in the sky, refining orbits of millions, including perhaps the next interstellar wanderer. These milestones were not only observational, they were tests. Each phase would narrow uncertainty, constraining models and guiding belief toward nature or artifice. In the deep quiet of interstellar night, 3I Atlas drifts onward, a grain of matter swallowed by the infinite. Behind it, the sun grows dim, the planets fade, and the signals of humanity dissolve into static. But somewhere, on a small blue world, its passage leaves an echo, not in the vacuum of space, but in the corridors of human thought. For centuries, the universe has spoken to humanity through silence, a vast, indifferent ocean where even the nearest stars seem unreachable, and where no sign of companionship has yet stirred the cosmic dark. Astronomers called it the Great Silence, a question so immense it haunts every generation. If life is common, where is everyone? But the arrival of 3I Atlas changed the tone of that silence. If this object is natural, then it is a testament to the wild artistry of physics, a wanderer forged in the birth throes of alien suns, its long journey shaped only by gravity, dust, and time. Yet if it's artificial, if its geometry, its motion, its endurance are the product of intent, then the silence was never silence at all. It was waiting. And we, unaware, have just heard our first whisper back. For philosophers and scientists alike, that possibility cuts deep. It suggests that humanity has already been observed, that somewhere beyond our reach, another intelligence looked upon our star and sent forth a machine to know it. Perhaps long before humans learned to walk beneath constellations, perhaps before Earth's continents had even settled into their present form. A probe, drifting for millennia, crossing the cold gulfs between stars with neither haste nor decay. It might not carry life aboard it, only purpose. Its mission, not conquest or contact, but observation. To witness, to record, to remember. Such an idea forces a new kind of humility, what astrophysicist Avi Loeb calls cosmic modesty. The recognition that intelligence may not begin or end with us. That consciousness might be as ancient as starlight itself, and that our species, though brilliant, is but a brief signal in a long and ongoing broadcast. If 3I Atlas is a message, it is written not in words, but in motion. Its trajectory across the solar system, a sentence carved in celestial geometry. Each deflection, each curve around the sun, a syllable in a language of physics. And in that sentence lies a question too large for any single answer. What does it mean to be known by something older than humanity itself? The response cannot come from science alone. It lives also in art, in faith, in philosophy, in every attempt to make meaning from the unknown. For some, 3I Atlas is proof that we are not alone. For others, it is proof that even if we are, the universe is still capable of wonder beyond imagination. Across observatories and laboratories, the data continues to flow. Spectra, spin rates, trajectories, numbers that will soon become history. Yet beyond the mathematics, there lingers an emotion few scientists speak aloud. Awe, because in studying this visitor, humanity has turned a mirror toward itself. What it sees reflected is both small and extraordinary. A civilization fragile enough to be humbled by a rock the size of a mountain, and curious enough to measure it atom by atom, photon by photon, in the hope of understanding its place in the infinite. The object asks a silent question. What will we leave behind? If this interstellar traveler is indeed artificial, then it carries the legacy of another species, their craft, their technology, their story, sealed against extinction. It is, in a sense, a monument, a testament that intelligence can outlive the stars that birth it. And so, by its example, we are invited to imagine our own endurance. When humanity one day sends vessels to other stars, machines built to outlast empires and suns, what will they say about us? What truth will they carry when Earth's continents are dust and its oceans vapor? Perhaps 3I Atlas is not a warning, but a blueprint. It shows that survival is not measured in years, but in persistence of purpose, in the ability to leave behind a trace that endures across cosmic time. In this way, the visitor becomes a paradox, a messenger with no message, a presence that speaks most clearly through its silence. Its very existence reminds us that life, intelligence, and meaning may not be fleeting accidents of chemistry, but recurring patterns woven through the universe itself. And yet, the questions remain. unsatisfied, unbroken. What is it for? Who made it? Where is it going now? Each question is a horizon, approached but never reached. Even now, as it fades beyond Jupiter's orbit, 3i Atlas offers no revelation, no signal, no final act. Only an invitation to look, to listen, to wonder in the grander frame. This is how humanity learns, not through certainty, but through curiosity sharpened by mystery. The object's passing becomes part of our own cosmic autobiography, a reminder that we are still children at the edge of an unfathomable sea, casting stones into the dark, waiting to hear what echoes back. And somewhere in that waiting, meaning begins. Perhaps the true legacy of 3i Atlas will not be found in what it is, but in what it awakens within us. A restlessness that transcends borders, disciplines, and generations. A longing to reach, not to conquer, but to understand. So it drifts onward, past the gas giants, past the heliopause, into the silence from which it came. Its path unwinds among the stars, a faint trace of reflected light against the black. For a time, humanity will follow it with telescopes and calculations, until even the best instruments lose its signal. And then, the cosmos will close over it again, a ripple fading into eternity. But the questions it leaves behind will not fade. They will haunt observatories and classrooms, echo through documentaries and dreams, linger in the hearts of those who still look upward. Because whether 3i Atlas is stone or sentinel, artifact or accident, its journey is proof of something profound, that mystery still exists, that even in an age of algorithms and data, the universe can still surprise us, still humble us, still move us to silence, and in that silence lies a gift, the reminder that wonder itself is the oldest and most human of emotions. As the object disappears beyond the reach of every telescope, the stars roll quietly above. The earth turns. Life goes on. Yet somewhere, in the deep night of thought, a realization flickers that in watching 3i Atlas pass through our skies, we were not merely observing a visitor. We were remembering our place, a species suspended between ignorance and infinity, learning slowly that the universe may not be silent after all, only waiting for us to learn how to listen. In a universe this vast, silence is not absence, it is invitation.